Welcome to our exploration of spin flipping and precession. These tiny but mighty phenomena are not just quantum curiosities. They are the foundation of technologies that save lives and unravel the mysteries of molecular structures. By the end of this lecture, you'll understand how the behavior of nuclei under magnetic fields leads to groundbreaking tools like MRI and NMR spectroscopy. So, let's begin. Spin is a quantum property of particles like protons and neutrons, often visualized as a tiny spinning sphere. However, it's not an actual spinning object. It's a quantum mechanical property that gives the particle angular momentum and a magnetic moment. When these particles are placed in an external magnetic field, their spins tend to align with or against the field. This creates two energy states, a low energy state aligned with the field, and a high energy state opposed to the field. To flip a spin from low to high energy, a specific amount of energy must be absorbed. This energy corresponds to a precise frequency of electromagnetic radiation. Spin flipping is the transition from one state to the other and is the basis for technologies like NMR and MRI. Let's explore the relationship between the two energy levels of a nucleus, alpha spin and beta spin, as a function of the applied magnetic field H0. The lower energy state is represented by the alpha spin state, shown in cyan. The higher energy state is represented by the beta spin state, shown in magenta. As the magnetic field H0 increases, the energy gap between these two states also increases. At H0 equals 23,500 Gauss, the energy difference corresponds to a frequency of 100 megahertz, shown by the green dashed line. Similarly, at H0 equals 47,000 Gauss, the energy difference corresponds to 200 megahertz, indicated by the orange dashed line. The slope of the energy levels indicates the proportionality of the energy difference delta E to the applied magnetic field. This diagram illustrates the two spin states in a magnetic field. In the low energy state, spins align with the magnetic field. In the high energy state, spins are opposed to the field. The energy gap between these states depends on the strength of the magnetic field and the particle's gyromagnetic ratio, a property unique to each type of nucleus. For example, hydrogen nuclei, used in MRI, have a high gyromagnetic ratio, making them highly responsive to magnetic fields. This diagram illustrates the concept of spin flipping, highlighting the relationship between ground and excited states in the presence of an applied magnetic field, H0. Ground state. The lower energy state is shown at the bottom, where spins are aligned with the magnetic field, H0. The blue arrows represent spins in the ground state, excited state. The higher energy state is at the top, where spins are aligned against the magnetic field, H0. The red arrows represent spins in the excited state. The transition from the ground state to the excited state occurs when energy, Hnu, is absorbed. This absorption causes the spins to flip their orientation, moving to the higher energy excited state. The applied magnetic field, H0, represented by the green arrow, creates the energy difference between the two states. The magnitude of H0 determines the gap between the ground and excited states. Electromagnetic energy transfer facilitates spin flipping by supplying the exact quantum of energy needed for a nucleus to transition from its lower energy state to a higher energy state. This transfer is governed by the resonance condition, where the frequency of the applied energy matches the energy gap determined by the external magnetic field. This principle is central to understanding how spin systems interact with electromagnetic radiation, forming the basis of NMR spectroscopy. This diagram illustrates the concept of precession of a rotating object. A spinning top or gyroscope undergoes precession due to the effect of an external force, such as gravity acting on its weight. While the top rotates about its axis, the axis itself traces a circular path, showing precession. In the presence of a uniform external magnetic field, a nucleus with spin exhibits magnetic properties due to its intrinsic angular momentum and magnetic moment. These nuclei orient themselves either parallel or anti-parallel to the field, producing quantized energy levels. This alignment and separation of energy levels underpin the concept of nuclear spin resonance. To understand Larmor precession, imagine a spinning top wobbling under the force of gravity. Similarly, a nucleus with spin precesses around the direction of the magnetic field. This precessional motion occurs at the Larmor frequency, which depends on the gyromagnetic ratio of the nucleus and the magnetic field strength. This analogy simplifies the complex quantum mechanics of nuclear behavior in magnetic fields. Spin flipping is achieved through resonance, where the energy of electromagnetic radiation matches the exact energy difference between the aligned and anti-aligned spin states of a nucleus. This phenomenon allows energy absorption and the subsequent transition between spin states. Resonance is a cornerstone in technologies like NMR, enabling precise analysis of molecular structures. Spin flipping plays a vital role in two transformative technologies. First, it serves as the basis for nuclear magnetic resonance spectroscopy, a technique that analyzes molecular structures by observing how nuclei respond to magnetic fields. Second, it powers magnetic resonance imaging, MRI, a medical diagnostic tool that uses spin flipping of hydrogen nuclei to generate detailed images of soft tissues, enabling accurate and non-invasive diagnoses. Precession plays a critical role in various scientific and technological domains. First, it underpins gyroscopic motion, which is essential for navigation systems used in aviation, maritime operations, and space exploration. Second, precession is fundamental to nuclear magnetic resonance, NMR technologies, where the precessional motion of nuclei in magnetic fields enables the precise detection and analysis of molecular structures. Spin flipping involves the transition of nuclei from the alpha spin state, aligned with the magnetic field, to the beta spin state, which is anti-aligned. This process is energy dependent and occurs when the nucleus resonates with electromagnetic radiation of a precise frequency. Resonance enables the absorption of energy needed for this transition, making spin flipping a cornerstone in nuclear magnetic phenomena and their applications. Precession describes the circular motion of a nucleus spin axis around an external magnetic field. This motion occurs due to the torque applied by the field on the magnetic moment of the nucleus. The frequency of this precessional motion is determined by the Larmor frequency, given by the equation omega equals gamma h0, where gamma is the gyromagnetic ratio and h0 is the strength of the magnetic field. This concept is fundamental to understanding nuclear behavior in magnetic resonance technologies. Resonance occurs when the frequency of electromagnetic radiation matches the precession frequency of nuclear spins, known as the Larmor frequency. At this precise match, energy is efficiently transferred to the nucleus, enabling spin transitions between energy states. This coupling of precession and resonance is fundamental to techniques like nuclear magnetic resonance, NMR, and magnetic resonance imaging, MRI, where energy absorption facilitates the analysis and visualization of molecular and tissue structures. The external magnetic field, H0, plays a crucial role in determining the behavior of nuclear spins. It dictates the alignment of nuclei, either in the lower energy alpha spin state, aligned with the field, or the higher energy beta spin state, anti-aligned. Additionally, the strength of H0 directly influences the Larmor frequency, which sets the resonance conditions needed for energy absorption and spin transitions. This relationship makes H0 fundamental to the principles of NMR and MRI technologies. Nuclear magnetic resonance (NMR) spectroscopy uses spin flipping to analyze molecular structures with precision. When nuclei transition between spin states, they emit signals that are specific to their chemical environment. These signals can shift in frequency based on interactions with surrounding atoms, offering detailed insights into molecular geometry, bond structures, and dynamics. This makes NMR an indispensable tool in chemistry, biochemistry, and material science. MRI, or magnetic resonance imaging, is a medical imaging technique based on nuclear magnetic resonance (NMR) principles. It produces high-resolution images of internal tissues, making it invaluable for diagnosing conditions in the brain, muscles, organs, and other soft tissues. Its non-invasive nature and ability to deliver detailed insights have made it a cornerstone of modern medical diagnostics. Gyroscopic motion, specifically precession, plays a crucial role in modern technology. Precession principles are widely applied in navigation systems, such as those in airplanes, ships, and even smartphones. These systems rely on gyroscopic motion to maintain stability and orientation, ensuring accurate directional guidance and balance. This technology is fundamental in devices ranging from GPS systems to drones and spacecraft. To summarize, we've covered several important concepts. Spin flipping. This refers to the transition between the alpha A and beta V states in a magnetic field, a fundamental principle in both NMR and MRI. Precession. The circular motion of magnetic moments around an external magnetic field is crucial for understanding resonance phenomena. Applications. These principles have wide-reaching applications, including NMR for chemical analysis, MRI for medical imaging, and gyroscopic technologies for navigation and stability in devices.